Hi, this is Chris Schomburg, and we're going to talk again about numbering systems and codes. We left off last time with, we talked about binary, decimal, and octal numbers. Now we're going to talk a little bit more about hexadecimal and how you would use that system. So the chapter overviews is you should be able to determine the weighted of each position of decimal, binary, octal, and hexadecimal numbers. You should be able to convert between these numbers because it's very important to do that in industry and those kinds of things too. So being able to convert between the four systems is important. So be able to describe a binary coded decimal system or BCD number. We're going to talk about those today. Translate between alphanumeric data and use ASCII. We're going to talk about that as well today. So this is a review right here. What is a digital signal and what is an analog signal? So digital signals are an off or an on state that can represent either a 1 or a 0, a high or a low state, 5 volts or 0 volts in that case. So it's a digital signal. An analog signal is a continuously varying signal, so it's something that is sinusoidal. It is actually on a spectrum, so like the number system, infinity to negative infinity, you can continue forever. So there's no real end or starting point. So examples of this are temperature, pressure, and velocity. Okay, we did ask you to think of 3 things that are analog and 3 things that are digital. And I talked about my friend who was in the military and noticed the camouflage just changed. And it changed to be a pixelated camouflage instead of what was a more analog approach, which was below here. You can see this. These are both analog approaches, and this is a pixelated or digital camouflage. We need to think of the 3 things that are analog and 3 things that are digital. We came up with a record player as an analog signal, and really why it's analog is that the record itself has the full signal or the full sound of the song on that record. And if you were to bump it or hurt it or make a chip in it, it's going to have that chip the whole time. So whenever you play that song at that point, it's going to always mess up. Okay, and so you might have something that would be like a broken recorder or something like that, or broken record is what we call it. A phonograph has the same problems and same challenges. Phonographs were invented by Edison, and he was the first person to create sound recorders. The VCR is the same way. The tape deck, like in a Disney movie that you're going to watch, is going to miss the video. It's going to you can have a hole in it or something like that, and it's going to have the same error at that same point every time. So CDs are compact discs, so they actually discretize the information. So that means that it is digitalized, so it's digital, and it is a digital signal. Shuffles, iPods, Androids, all kinds of devices that are now used today are digital. This is a digital picture right here, and in 2007 you could see the differences between a film picture, which is analog, and a digital picture, which is using pixelated 1s and 0s, and it actually has a sensor on it that it goes to, and that sensor is electronic. In 2007 you could see it was getting close to being as good as film, and now today professional photographers almost always are using digital cameras. So we have analog versus digital. You can see the camouflage up here. This is the analog camouflage. This is the digital camouflage. We had analog circuits with our watches we talked about. And so we had an analog watch. It has a sinusoidal continuously changing variable, and we have a stepwise voltage versus time, and you can see it is a step function, or actually on or an off state. So we can look here. This is an on state, this is an off state, this is an on state, this is an off state, this is an on state, this is an off state. So it's either a 1 or a 0 essentially. Okay, so now we're going to go into hexadecimal number systems. And really the only difference here, we talked about binary, which was a base 2. We talked about decimal, which was a base 10. We talked about octal numbers, which was a base 8. So now we're talking about a base 16. And so really what are the allowable digits is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then you go to A, B, C, D, E, F. And so then really what we have in the hexadecimal system is we have each hexadecimal represents 4 bits of a group. So 2 hexadecimal digits are used to represent 8 bits, and 8 bits are called a byte, and 4 bytes are called a nibble. So this is kind of the important thing here. So what we're looking here is we have our table, and in this case it has hexadecimal on the right hand side. So you can see 1 through 9 hexadecimal and decimal look identical. And then we go into this 16 segments. So we have A, B, C, D, E, F. And so 10 through 15 is different, but then it will repeat itself in this segment. So we see that right here. Then we see the 0 or 1, 0, 1, 1, 1, 2, 1, 3, 1, 4. So we see a repeated signal. So what we're going to do is we're going to look at a binary to hexadecimal conversion. So we're going to group the binary bits in groups of 4. So first thing we're going to do is start with the least common bit. So our lowest common bit, is right here. So that is, you can tell this is binary because there's a subscript of 2. So it's 1, 0, 1, 0. So we go back. We look at the binary to hexadecimal. Okay, so it's 1, 0, 1, 0. So it is 5. Okay, so the first group is 5. Okay, then we go 0, 0, 1, 1. So if we go back, 0, 0, 1, 1 is right here, so that's C. So we have C, and then our last one, if we look at it, it's just 1, so it's going to be 1 down here. So that's how we do that. So we group it into groups of 4. 1, 0, 1, 0, 0, 0, 1, 1, and 1. So we should get 1C5 in hexadecimal. So how would we convert that to binary? We could do that the opposite way. This is just to check to make sure we did it right. So you go 5 is 1, 0, 1, 0. Why is it? That's what I asked you the first time. Why is that true? Let's check and make sure. So 2 to the 0 is 1. 2 to the 2 or 2 to the 1 is 2, but it's 0 here. 2 to the 2 is 4. So 4 plus 1 is 5. So that one makes sense. Okay, then we have this one. So we have 0, 0, 1, 1. So 0 would be 2 to the 0 is 1, so that's not there, that's a 1. 2 to the 1 is 2, that's not there. 2 to the 2 is 4, plus 2 to the 3 is 8. So 8 plus 4 is 12. So let's go back, look at 12 right here, and our binary is a C. So that's correct. And then our last one, it's just 1, 0, 0, 0. Because you have 4. So it's 1, 0, 0, 0. So because you have 4 bits. So that's a 1. So that makes sense. So let's do a hexadecimal to decimal conversion. Remember, you use the weighted base as a weighting factor, and our base is 6. So we're converting 9CFH to base 10. So what we do is we're going to multiply each one out. So the least significant bit is right here. So the least significant bit is right here. We're going to do 15 times 16 to the 0. Well, 16 to the 0 is 1, so that's 15. 12 times 16 to the 1, it's 192. 9 times 16 to the second power is 2,304. So we add those all up, and we should get 2,511. Let's just make sure that I did the math correctly. But yeah, so let's look at that. Okay, so the first one was right, so we know 15 is right. 12 times 16 is 192, that looks right. And 9 times 16 to the y2 is 2,304. We add that, and we get our answer, which is 2,511 in decimal. What? Wait, just a second. Yeah, 2,511. So that's actually the correct answer. So let's check that one more time. Let's go 15 plus 12 times 16 plus 9 times 16 to the y2 is equal to 2,511. That is correct. Okay. Decimal to hexadecimal conversion. Method 1 is to convert decimal to binary, and then binary to hexadecimal. Method 2 is to do successive division with the base 16. So convert 500, which is a decimal number, into a hexadecimal number. So we can do successive division and turn it into a binary number and then convert it to a hexadecimal number. So the first thing we do is we take 500 divided by 2, we get 250, the remainder of 0. That's our least significant bit. And we have 250 divided by 2, we get 125, remainder 0. 125 divided by 2, we have a remainder, so it's 1. So we get 62 divided by 2 is 31, we have a remainder of 0. 31 divided by 2 has a remainder, so we get 15, and we have a remainder of 1. 15 divided by 2, we get 7.5, so we have a remainder of 1. 7 divided by 2, we get 3.5, we have a remainder of 1. Again, we're using the number from before, 3. We get 3 divided by 2 is 1.5, we have a remainder of 1. And then we end up taking 1 and we divide by 2, and we get a remainder of, so we have 1. So our number is 0, 0, 1, 0, 1, 1, 1, 1, 1. So it's 5 ones. 0, 0, 1, 0, 1, 1, 1, 1, 1. And that is our binary number. Now we just need to convert it to the hexadecimal number. So what we're going to do is we're going to group it into groups of 4. So we have 1, 2, 3, 4. So this one is 2 to the 0 is 1. It's not there. And then we have 2 to the 1 is 2, which is not there. Then we have 2 to the 2 is 4. So that first number in hexadecimal will be 4. So 1, 2, 3, 4. We go to the next one. 1, 2, 3, 4. It's all ones. So we know it's F. And so we know it's 15. Let's check that just to make sure. Okay, so 2 to the 1 is, or 2 to the 0 is 1. 2 to the 1 is 2, that's 3. 2 to the 2 is 4, that's 7. 2 to the 3 is 8. So 7 plus 8 is 15, and that is our number. So that's how we know it's 15. So 1, 2, 3, 4. This one is just a 1 by itself. We know that that is 1 in hexadecimal. So it should be 1F4. Four. 1F4 is our hexadecimal number. And so that is our hexadecimal number. We write a base 16 as a subscript to note that we're using a hexadecimal number. Okay, the second method is swifter, but you really have to be careful about your division. So what we have is 500 divided by 16 is 31 with a remainder of 4. It's our least significant bit. Then we have 31 divided by 16 is 1, remainder of 15, or F. Then we take 1 divided by 16 is 0. We get remainder of 1, with that being our most significant bit. So we have we have 1F4, and that is in hexadecimal. And that's the same process, we just had to do long division to get there. So the method 1 was to convert the decimal number to binary, and then binary to hexadecimal. This is method 2, using the successive division of the base, which is 16. Okay, so what I'd like you to do today, or be ready for, is to be ready for a review, problems 1 through 22 and 1 through 27 on page 17, and that's what we will be ready to work on. Prepare for quizzes, and we'll see you in class. Okay. So what is a binary coded decimal system? BCD number. Each of the 10 decimal digits is represented by its 4-bit binary equivalent. So decimal to binary coded decimal conversion. So convert each decimal digit to its 4-bit binary code. So BCD to decimal conversion, and reverse the process. So really what we're looking at here is a BCD right there is in the table. So what we're looking at is we have a binary code right here. And as we go to 10, what we're looking at is it's represented in each 4-bit code. So this is 1 and this is 0. That's representing 1 and 0 here. And this one, if we look here, 11, this is 1 and this is 1. So that's 11. This is 1 and 2, so what we have here, 1 and 2. Okay? And so that, so on and so forth as we go down. Really what we're representing is we're representing each bit of the decimal is represented by 4 bits in the BCD system. So we should have, it's kind of like if you think of the number system with digits, this is the ones digit, this is the tens, and so essentially what you're doing is you're creating that with the 4 bits. So we have 1, 2, 3, 4. That is representing a 0. 1, 2, 3, 4. That's representing a 2. So that's what we're representing with the BCD numbers. So the ASCII, or American Standard Code for Information Exchange, represents alphanumeric data, and it uses 7 bits. There are 128 different code combinations. 3-bit groups is most significant, and a 4-bit group is least significant. So what I'm talking about here is really, this is in your book, it's another table that we're going to use. And so what you have, the 3-bit code, if you look back, said is most significant, and the 4-bit code is least significant. So if we start with our least significant code, and let's say I want to write out my initials, I could say C, so I'd have to write 1100 and then 001, because that's the most significant bit. So that's kind of how you explore how to use this text conversion essentially. So it's a text or number conversion that you can use by using the least significant bit, which is 4 bits, and then 3 bits in the most significant bits. Okay, so really I'm going to write out my initials using ASCII. So what we have here is we have C, we talked about before, which if we look again is 1100 and then 001. 1100 001, and that's our C. That's the letter C. W, if we look at W, it's right here. So really all we're looking for is we're going to look for the least significant bit. And I apologize, it keeps erasing. So we go here, that's 1110, 1110, and then the most significant bit is 101. It's 101. Okay, then we look at the least significant bit for my last name, which starts with an S. So we're going to look for S on here, and it looks like if we go over, it's 1100, 1100, and then the most significant bit is 101. So 1100, 101. And so that is our groups. So we have our groups of most significant bit and our least significant bit that comprise of the ASCII. Okay, so there are really quick ways of doing this. You can find tools to convert these online very quickly, but I caution you to do that. I think it's important to go through the process and know what you're learning and really have a good comprehension of what you're doing. Plus, practice is really what makes perfect. So really doing a lot of practice is what will get you in a better state for the test. Okay, so here's what we're going to do. We're going to look at an application problem, and in this case, the application problem is we have 4 tanks, and each of them represents either pressure sensor or temperature sensor. And so really, they're going to use binary codes to designate what we need to do. So really right here, we have P, T, P, T, P, T, P, T. And they correspond to tank D, C, B, and A. And right here, it looks like D is our most significant bit, and A is our least significant bit. So we have a binary code right here that was read. This could be something that you read as a technician, and you then need to see from the binary code what the error is. And so there are a lot of older computers out there that do a lot of tasks, and so it's not unlikely that you're going to use an older computed technology to work on tasks in industry. In fact, one of the things that I think is really remarkable about electronics is that it's really an industry that was made in the 1800s and 1900s. So there's a lot of new innovation that needs to be done to update that technology. And so that's something you might need to think about when you're doing this kind of stuff. Okay, so we have 0001, 0100. That's our code. So if we put it in here, the zeros indicate that it's not a problem. So what we're going to look at is that we have a 0001, so we have P, the pressure sensor in tank B is high, and then we have a 01, and the pressure sensor in tank C is high. So tank C and B pressures are dangerous. So that's what we can get from this application problem. Okay. Okay, so on another problem that's very similar to this one, if you look in your book, we could actually have a hexadecimal number represented or a binary number represented. And so what we could have to do then is we can convert the hexadecimal number into binary, and then we result in that code. So okay, so we have a hexadecimal number, and we know that's hexadecimal because we have a H there for hex. So we have 5. So really, what is 5? So 5 would be 101, and how we know that is 2 to the 0 is 1, 2 to the 1 is 2, which is not significant there. It's 0. And then we have 2 to the 2, which is 4. So 4 plus 1 is 5. And so we have that for the first 4, and then we have that for the second 4. So we know that we have a hexadecimal number of 5, 5. So what we're looking here is you first have to convert it from the hexadecimal to the binary number. Then the next thing you can do is once you have the binary number, you can then convert that into whatever temperature or problem there is. So if we look at it right here, if you have a 1, 0, 1, 0, 1, 0, 1, that means the temperature all the way through is the sensor that's high. And so that's why we know that all temperatures in this are dangerous. So that might be something that you would look into, is being able to convert these types of signals to represent a more important safety or concern. So what is the octal number if the tank B has a high pressure and temperature? So if we look here, tank B is right here. So that would be a 1, 1, 0, 0. Octal, remember, octal we talked about last time, and that's bits of 3. So what we have here is we have octal is bits of 3. So what we have here is we have tank B has a high pressure and temperature. So we have a high pressure, which is PB, and temperature, which is TB. So right there, these two are 1. So we know if we look at bits of 3, that's 0, 0, 1. We look at our octal, our binary, 0, 0, 1 is a 4 in octal. So we know it's a 4. And then we have a 1, 0, 0, 0, 0, which is a 1. So that's 14 in octal. So that's correct. It's 14 in octal, and that is our binary number. Okay, numerical quantities occur naturally in analog form, but must be converted to digital form to be used in computers or digital circuitry. The binary numbering system is used in digital systems because ones and zeros are easy to represent by ons and offs in transistors, which are outputted in zeros or 5s volts. So 0 for 0 and 5 volts for 1. And so really that makes it a very efficient system because transistors can switch on and off very, very quickly. And so that's something that allows computive technology to be very efficient. Any number system can be converted to decimal by multiplying by each weight or each digit by its weighting factor. The weighting factor for the least significant digit in any numbering system is always 1. Binary numbers can be converted from octal to form groups of 3-bit hexadecimal by forming groups of 4 bits. The binary coded decimal system uses a 4-bit drive decimal displays, such as those in a calculator. ASCII is used by computers to represent all letters, numbers, and symbols in digital form. Okay, hopefully you're hanging with me through this flipped lesson, and we hope to see you next time. Again, these are prep lessons that you can watch a little bit ahead of time, and hopefully you can use them for future reference.